Good morning. This is Tim Stewart. I am president at Visual Decisions, and we are here today to talk about different approaches to collecting information from the shop floor to use for improving performance. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve operations since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements, such as 30% increases in OEE, 50% scrap reductions, and much more. But just like wearing a Fitbit won't automatically make you thin, implementing any of these different technologies for the shop floor won't automatically make the business better. The culture of the organization and business processes have to be adapted to take advantage of the new capabilities to drive real improvements. With that said, let's get started. As a quick note, if you have questions during the presentation today, please enter them into the Q&A. Also, the presentation will be available, as well as the recording of the presentation will be available afterwards at my website at visualdecisions.com. All right, so let's start off with a comparison of these different systems between MES or OEE systems or IoT platforms. So if we look at some of the different shop floor data platform alternatives, some of the primary ones that are out there are MES systems, which have been around for 25, 30 years, somewhere in there. And have some very, very well-known brands, Rockwell, Aviva, IQMS, Active Plant, etc. Then you have dedicated OEE solutions. And some of these OEE solutions have been around for at least 20 years now. Worked with a number of these systems in the past as well, implementing them to gather that information from the shop floor to utilize for improvements. And then you have IoT platforms such as PTC ThingWorx, Siemens, Software AG, C3. Inductive Automation calls themselves an IoT platform at this point. They're truly more of a SCADA system, which is another class of software. But there are a number of alternative systems that, and too many to really go through today. But if you have interest in other systems as well, other types of systems, please reach out to me and I'd be happy to go through those with you. So the primary strengths of each of these different types of systems. MES has been around, as I said, for decades now. It's had all of that development and refinement behind it. It's extremely well established. So there are ISA standards around the different functionality that is provided within the different solutions. They have very well established data models because they've been around for so many years now. They have a number of kind of out of the box integrations. You'll still need to configure and so forth, but those integrations do exist. MES or MOM, depending on the vendor, really has a broad suite of solutions that are part of that. And so you get a lot of potential functionality with these systems. They're built to act as a system of record. So if you have needs for validated environments, for track and trace, for product genealogy, things like that, an MES system is truly the best fit, out of these different solutions. And then you can also have kind of a standard common system across your different sites that, as much as possible, you can have that same structure for your manufacturing data across your different manufacturing facilities. With IoT systems, generally, they're much more modern architectures. They're nearly infinitely flexible. It's a platform, and essentially it's a development platform that has, certain built-in functionality with it. It's built for connectivity, and so connecting up to the machines, to sensors, to test equipment, to anything else. There's a reason why it's called the Internet of Things, because it is built to connect to just about anything that you have out on the shop floor. It's also built essentially as a system of improvement. So whereas an MES system is built as a system of record, and you want to have every single transaction that happens on your shop floor flow through the MES as a result of that, an IoT system is much more intended as a system of improvement. You capture, the information that's relevant to improving operations, as opposed to trying to capture, every single transaction that's happening on the shop floor, although it can be used that way as well. It's also built as a hub for the shop floor. These systems don't necessarily look to own the data that they're collecting. It can be used to certainly persist that data into a database, but for the most part, it's looking to get that information, perform some action, notify, etc., persist the data, pass it to another system, integrate, and orchestrate between different environments. And it can easily be the center of best-in-class solutions. And so, very much if you have different point solutions on your shop floor, maybe different test systems, quality systems, maintenance, etc., the IoT system can very much be a system that acts as a hub for all of those different environments. And then it also easily coexists with those other systems. OEE solutions are a little bit different here. The technology maturity varies. And so some of these have been around for, as I said, 20 years now. And some of them are actually quite new and very much focused on the machine learning aspects of being able to do predictive maintenance and so forth. Which brings me to the next point, that there's two primary approaches for analysis. One is that these systems can present to the user various graphical analysis, different reports and so forth, to allow the user to kind of mine that information for, where are the issues on the shop floor, what needs to be done, what are the reasons behind those different issues and so forth. And the second is a machine learning focus, where the system is collecting very detailed data from the process, and it is analyzing that information and then basically presenting to the user what is the probability of some event occurring, usually predictive maintenance, predictive downtime. And so the two different approaches for data collection that are used for these, the machine learning focused applications very much want just that machine process data. And very often these systems will not even have an interface for the operators to enter additional contextual information. They just want that machine process data. And then you have the flip side of that, where some of these kind of older school OEE systems really collect the event data from the machine. So is it up, is it down, is it producing parts, how many parts is it producing, et cetera. And then look to the operators to provide context for when the machine goes down, why did it go down? And so two very different approaches for data collection, for analysis, and so forth. And these are very much built to act as systems of improvement, as opposed to systems of record that contain significant out-of-the-box functionality around analyzing machine uptime, downtime information, and somewhat quality information as well. Although, to be honest, most of them are pretty thin on out-of-the-box functionality around quality, and they are by far the quickest to implement because they're the most limited in scope and kind of the simplest solutions. The primary weaknesses of each system, MES is typically a much more rigid structure, has very often longer implementation time. There's kind of standards out there for implementing MESs, and you're generally not going to get the first plant up and live. Within 12 months, it's possible, but it's typically that long or longer. And then, there's a lot of complexities around implementing MESs, especially if you have a multi-plant environment and you're trying to balance the needs of the different plants, but you want as much standardization as possible. It's generally expensive to buy and implement these systems, and it can be overkill for simpler needs. It can be difficult to have an absolutely common solution across the facilities. And so while these are often built to have that common structure, common data structure across your different facilities, if you have certain plants that make widgets and certain plants that bottle water or something, it's really hard to have that common solution that fits the needs of all of your different plants. And then they really want to be the center of the manufacturing world. It's difficult to use these as secondary systems. They are meant to be the primary system for data collection and data housing, and they want to own all of that data because they are meant to be systems of record. With I-IoT systems, the weakness is that you're buying a toolkit. There's going to be very little functionality that's out of the box, and you really have to staff up to build the solutions on top of these, or hire external help to build them. So the upside there is that you can build anything with it. The downside is you have to build it. And then with OEE Solutions, depending on which one you go with, the technology maturity varies significantly, but the upside of the out-of-the-box functionality is that you have significant out-of-the-box functionality, but the downside is that you are boxed in. You're very much limited to extend most of these systems. They do what they do, and the only addressed use cases for which they were intended. So as I go through the presentation today, I'll talk about a lot of different use cases to utilize shop floor data, and these systems don't handle a lot of those. And it also exists as a data island. They are meant, they're designed to store their own data, and if you want to access that, you're going to have to build a custom integration to get to it. So with all of that said, let's look at kind of creating a complete profile of data from your shop floor. Data originates at every step in the value chain, no matter what system you're putting it into, all the way from receiving, whether that's on time and full, sample tests, logging on performances, how you receive it into inventory, those transactions and so forth. If you have serialized things that are coming in, or lot stamped things that are coming in, all of that information is available if you choose to record it. And then all the way through each step in the process, there's information available within the PLCs or controllers for all of the different machines that are being utilized. There's labor information that's available. There's all kinds of different things that you can collect if you choose to do so, all the way through shipping. And so what this means is that operations data can reside across a broad array of different systems. And so one example that I talk about often is that we were asked to create a corporate quality dashboard at one of our customers. And we initially, were talking to IT and said, where is the quality data? And they said, oh, it's all in SAP. And when we got done laughing, we said, no, really, where is, where's all the data? And they said, it's all in SAP. So we started talking to them about warranty. And they said, oh, well, we have a custom developed warranty system that, is built on SQL Server that, runs, in our, warranty repair center. Great. Okay, that's a second system. What about your external warranty repairs? Oh, we have a separate database for that one. Okay, great. That's 3. What about the, plants that, built these other products? Oh, they use separate access databases in each one of those different plants. And so then that was up to 5 different systems. And so we just kept going from there for, non-conforming material, for statistical process control, for test systems, for laboratory information, for, all kinds of different things, as you can see here. And in the end, we found 57 different systems just for the quality data itself. That doesn't count the fact that a lot of the production information that you can capture, what's happening on the different machines as production is being done there, can influence quality. And so you want to access that information as well. These were just 57 systems for quality alone. And so when you look at these things, the purpose of an MES is to eliminate a lot of these different systems so that you can have one. The purpose of an IoT system is that it can talk to all of these different things and coordinate the exchange of information between them. And then the purpose of an OEE system is to improve OEE, and it doesn't really care about what's happening in all these other systems. Data contextualization. Instead of looking at information coming from a machine or sensor on an island, how do you contextualize that information? How does that fit within the product hierarchy for whatever you're building? How does it, fit within the bill of material or the recipe? For the materials that are being consumed, who were the suppliers, and what purchase orders did that information come in on? What are the different elements of cost that are associated with that? And so all of these different things can contextualize the information that you're getting from a machine or from a sensor. And again, an OEE system is going to look at that data basically as that data. Whereas you have an IoT system that can pull all of this information together, any of it that you want. And an MES system basically has a predefined structure for the information that you will be collecting. Real quickly on different types of data, you have diagnostic metrics, you have you have performance metrics, and you have financial metrics. And the difference between these is pretty plain, but just to make that a little bit more clear, something like first pass yield is a performance metric. And first pass yield is extremely useful measurement to be able to look at my quality within an operation and to be able to make a judgment of, are things going well, are they not going well? Am I winning or losing in a given day? And if I can see that my first pass yield went from 97% to 93%, I know that something went wrong, but it doesn't actually help me improve the process because I don't know what happened. And so the diagnostic metrics are collecting the additional level of detail that help you understand, when a failure occurred, what was the failure that occurred. It's also collecting the process data from the machines and so forth, so that you can actually do that deeper root cause analysis to be able to say, when we see this type of fluctuation in the process as the machine is doing the operation, then we can probably guess that we're going to have cracking problems. And then kind of the way that some of these different things fit together is that you have diagnostic metrics kind of at the lowest level. You have the performance metrics that roll that information up. And then you can turn that into financial metrics if you understand how to make that conversion. So performance metrics, whether it's earned hours versus standard hours, productivity numbers, OEE, OLE for overall labor effectiveness, first pass yield, rolling throughput yield, machine utilization, etc. All of that information can be translated into a financial metric if you know how, and if you have the right data available to you. So all of these things kind of feed each other and or different sides of the same coin, but you have to see how all those things fit together, and then you have to have a system that's capable of making those translations. Some of these systems are going to provide machine learning, artificial intelligence, and some of them will not. In general, MES systems, according to the ISA 95 standard, do not include this information, but most of the major MES vendors provide other systems along with the MES that can provide that type of support. The IoT platforms, I think, all universally come either with that embedded or with extensions that allow that. And the OEE systems some are built around this functionality, and some of them don't support it whatsoever. And so what you get with those different systems, you have to pay pretty close attention to. Some examples of different use cases. Certainly predictive maintenance is by far the most common use case for artificial intelligence or machine learning on the shop floor. And it's the one that gets most of the press these days, so to speak. But it's also used for vision systems for inspection. It's used for predictive tooling, for predictive quality, furnace efficiency, monitoring different lubricants and filters and predicting when you need to do a change on those, or being able to analyze what's happening with those. There are safety applications, paint shop monitoring, warranty and shop floor analysis to tie that information together. There's cooling system monitoring and all kinds of different applications for it. And next week, we're actually going to talk about this for the whole presentation of different applications of machine learning outside of just predictive maintenance. One additional thing that you can do with this is to automatically identify, classify, and prioritize. So old school MES, old school OEE systems, and the IoT applications that a lot of people develop really count on the user, place the burden on the user to go through the different reports and graphs and so forth to identify where problems are occurring and why they're occurring. With these different machine learning applications, what can be done is to really identify where you have issues, and then be able to classify those into different failure types, different failure modes, and so forth, and even prioritize what is the scale of the issue, which ones should be done first, and so forth. And so these systems can be utilized to do a lot of kind of the basics, and then provide a list of different things to the user that they need to pay attention to. Some different custom analytics and workflows that kind of show the power of having an IoT platform as opposed to the kind of pre-configured solutions with MES or OEE. One of the things I talked about up front is that just knowing what happened and why is not enough. And the analogy that I use here all the time is a Fitbit. I've been wearing a Fitbit for 8 years, and I weigh probably 20 pounds more than I did when I started wearing the Fitbit. And it's not the Fitbit's fault. It's a great example of an IoT device. It collects all my steps, collects my heartbeat in real time and so forth, pushes that information to a cloud-based application. It has wonderful analytics in there that can interpret that data and tell me whether I'm awake or sleeping, how good my sleep is, what types of activities am I doing, and so forth. And then also has nice charts and graphs and everything else to allow me to interpret that information. So it's really not the Fitbit's fault. It does all of those things really well, but I haven't changed my behaviors. And because I haven't changed my behaviors, I still haven't lost the weight. And it's the same thing with any of these systems on the shop floor. They can, collect all the information, they can, present it to you and so forth. But if you don't change the behaviors of the people within your organization, you won't get the benefits you expect from these different systems. And so one of the things that you can do to influence that is to track the actions that you're taking from within the system itself. And so a lot of companies use spreadsheets. If you're in lean, common phrase is a bowler for tracking the different kind of lanes that people are working on, different projects and so forth. And it's very much separated from the collection of the data itself. Well, if you're building an IoT system and so forth, you can actually build that into the system itself so that you're collecting information and tracking your projects in the same place. And then you can actually look at the success of the actions that you're taking, comparing that to the information that you're collecting directly from the machines and so forth. And so you can build workflows into these solutions that bias people towards taking action on the data that you're collecting. You can also build kind of discovery analytics and guided analysis. So I talked about the machine learning applications being such that they can provide a list of different things to pay attention to the user. But these systems can be built in such a way that you can provide that slicing, dicing kind of free-form analysis point of view to the user, as well as guided analyses around particular topics, or around just what are the problems. So the exception analysis, or single topic things. And some examples of those guided analyses. If you want to do a setup analysis, you can actually have information collected about everything that you do within a SMET analysis. So for instance, if you attach an RFID chip to the different elements of this, or even people's badges and so forth, you can automatically spaghetti chart what are the movements of the materials, what are the movements of the people, and utilize that within your SMET analysis. And so there are individual workflows that you can put in place and guided analysis that you can do around things like setup analysis, or real-time value stream mapping, or tooling analysis, looking at your scheduling versus your production and so forth. You can build workflows around preventive maintenance to measure the effectiveness of that, but you can also do it around autonomous maintenance, as we'll talk about a little bit later. Another example is to create a living FMEA, failure modes and effect analysis, for people that aren't familiar with the acronym. And these are very useful analyses that you can do that look at, what are all the different potential failure modes, either for a process or a product. And for either one that you're looking at, and we'll talk about process since we're primarily talking about shop floor data, and you're looking at what are all of the different ways that this process can fail, what's the probability of that occurrence, what's the severity if that failure happens, what's my probability of detecting that failure, and then multiplying those three factors together to get a risk priority. And then you have a set of recommended actions that can be taken based on these different failure modes. Well, as I'm collecting this information, whether I'm using an OEE system, MES, or an IoT system, I can actually tie this FMEA to those systems if for the failure modes that I'm collecting from the process itself, I utilize the failure modes from my FMEA in my system to collect that information. So now if I'm doing that and I have that alignment, what I can actually see in my system is that I'm collecting those different failure modes, and I can start to Pareto out for each of those different steps in the process and so forth. What are the, what's the probability of occurrence? So how often does this fail? What's the severity? How long does this stay down for, and so forth. If I'm utilizing an IoT system, I can actually integrate with like safety systems and so forth that track whether that created a safety hazard and so forth, and look at the severity in a variety of different ways. And then I can also utilize the systems to increase the probability of detection. So there are different ways to do that, and I've talked about that in other presentations, but being able to utilize the data from any of these systems to kind of inform the FMEA is great. What you can do with an IoT system is actually build an FMEA application right in your IoT system that has this information live and updated at all times right within your IoT system. Reducing variance is another huge thing that you're trying to do in manufacturing. And so if we look at the causes of variation, you have variation from the machine itself. And all of these platforms are designed to look at the downtime, the quality that comes from the machine. IoT is probably the most extensive with those, looking at not only the impacts on the downtime, but also the quality and other factors and so forth. But all of them are meant to do this aspect of it. Where the MES and the OEE systems don't provide as extensive support is around other sources of variation, such as manpower or methods and so forth. And so how do you actually deliver work instructions to the line? How do you make certain that people are actually adhering to them and detect deviations from the standard work and so forth? And you can build all of that into your IoT system. Once again, you have to build it in. Supporting Kaizen process. Every step in a typical Kaizen process can be influenced by the information that you're collecting from these different shop floor systems. Whether it's identifying, what problems are happening and what the scale of them is and what are the impacts on the plant financials and so forth, to analyzing that process, brainstorming different solutions and expanding the solution space, testing those or possibly even simulating those changes before you put them in the shop floor, measuring and analyzing the results, and then standardizing that solution, both within standard work as well as across your operations. Being able to do root cause analysis, whether it's something like 5 whys or something as sophisticated as doing ANOVAs or design of experiments and so forth, or tying in the machine learning applications and so forth. But the root cause analysis is supported by all of these different applications in different ways. Maintenance workflows. I will say that MES systems have integration with some major maintenance systems like Maximo and so forth. But the one that's going to do by far the best job here is IoT, if you program it to do so. But you have the capability of doing things like supporting autonomous maintenance and creating a list of what are the tasks that the operator needs to do on a daily basis, based on either the condition of the machine or how many pieces have been run, et cetera, and being able to integrate that information to your maintenance system to say that these tasks have been completed and so forth, and build all of that into the standard work that you're supporting with these systems right there at the process. Preventive maintenance and being able to look at what PM tasks are defined, looking at the information from the process and building up an analysis around, do I need to do this PM task? Is it being done at the right frequency and so forth? And really optimizing your PM for the process and so forth, and doing as much as you need to, but no more. Condition-based maintenance, that's where you're monitoring like the temperature And once my temperature exceeds a certain point, maybe then I change the oil or the hydraulics or whatever else I'm looking at, or I'm monitoring vibration or power draw, and utilizing those things to determine when maintenance needs to be performed, but before a failure occurs. And then predictive maintenance is being able to do the same condition monitoring, but now making actual predictions, combining different elements of data to be able to say, what is the exact type of failure mode that I see occurring, and being able to make that prediction without having to have somebody say that when my temperature exceeds this number, I'm going to do maintenance. This is taking that to analysis to the next step, where the application itself will tell you that you have a likely failure coming up, because we see the temperature increasing as well as increased power draw and things like that. When you do have a failure, being able to do reactive maintenance in a better way is something that you can also support with an IoT system very effectively. So once that failure occurs, making the operator aware immediately, even if they're not in the vicinity, is something that is very simple. Being able to do some upfront diagnostics on the type of failure that has occurred, and letting the operator know, is this something that they can handle themselves? Is it something that's just jammed and they need to clear the jam, or is this something that is a deeper issue that needs a maintenance person to respond? Being able to integrate with other systems to let maintenance and engineering know not only that the failure has occurred, but what is the type of failure, and what are the tools that are needed, who should be assigned, things like that. Getting someone assigned, have to wait for that worker to become available, then they have to travel to the machine. So now once maintenance actually arrives, that was our mean time to respond. Now we have the other portion of mean time to repair, which is the actual repair. So then maintenance normally would have to diagnose the issue, but if that can be done up front through the AI machine learning, then that part can be skipped as well. And then they have to actually fix the issue. So at that point, the problem is fixed, or they have to come back. So why wouldn't it get fixed on the first try? The wrong repairman might be sent, for an electrical problem versus mechanical, as an example. They couldn't diagnose it on the first try. They don't have the required parts in stock. They have to leave the machine to go get parts from inventory. They might not have brought the right tools. They might need additional assistance, or they might not know how to make the repair. And each of these things can be addressed reasonably straightforward way with an IoT system. You can use the data from a lot of OEE systems to do these things, but they don't have that workflow, and you can't extend the application. You have to build that workflow in something else, utilizing the information from that OEE system. Some closing thoughts here. So when we at Visual Decisions work with customers and kind of define how to utilize information from the shop floor to improve operations, the first thing that we try to do is to map out the vision. If the customer already has that defined, great, we can utilize that. But we really need to begin with the end in mind. If you're Stephen Covey, 7 Habits of Highly Effective People fan, and have that map and have that vision, do that gap analysis to understand what do we have in place today and what do we need to add. Everybody has data from their shop floor, so how can you utilize the information that you have more effectively to embed that into the process, how you do your shift change meetings, how your quality department functions, etc. Filling capability gaps. That's where you implement one of these other systems in order to collect the information that you require, and then integrating across different processes. The example I use here all the time is I can look at my warranty information just on its own, but if I look at that warranty information and I see what was happening on the shop floor, when that item or that lot was produced. I can take that back into product design, product engineering, and look across, all those different processes, and that will help me really reduce the amount of things that end up in warranty. But everything that I'm doing here on the left side, again, the Fitbit example, doesn't get me the value until I do the stuff on the right side, which is to transform my culture and my process to take advantage of these new capabilities. So again, how does my quality department do their work and utilize this data? How does my continuous improvement team change the way that they run Kaizen events to take advantage of the data and so forth? How do I change the standard work for my operators, my supervisors, management, et cetera? And so, all of these things we can put in place to help our customers actually get the value that they expect from these solutions. Part of how we begin that, if they don't have that map already in place at the beginning, is to do a workshop to create that roadmap. And I won't go into the details here. I did a presentation a couple of weeks ago on this, but usually takes for a defined scope within a week. It can take longer than that for large organizations, et cetera. And there's a lot of value in doing that and having that vision, and then being able to communicate that plan out to everybody. So with that, I want to thank everybody for attending. Let me check the Q&A to see if there were any questions. There were not. And so with that, I thank you all. And as I said, the presentation will be available on my website. So you'll be able to download a PDF copy of this presentation, and the recording will also be made available there. So thank you, and I'll talk to you next week about machine learning applications in manufacturing beyond predictive maintenance. Thank you. Bye.